Hi, today we are talking about convergence really, but within convergence we're talking specifically today about the ratio technique. This will be the most used technique for determining whether a series converges or not, which will answer many more questions about series for us. So we don't recall. This is what we know. I'm telling you this now. For a geometric series, whatever the terms are, if the ratio R of adjacent terms, so like these two terms, the ratio, is less than 1, then the series converges to a finite number. If the absolute value of R is bigger than 1, then the series diverges. So here's your basic ratio test. And you have to know the ratio test, but like I said, this is the most used, so you're going to see this quite a bit. You will get quite used to it. So as long as that ratio is less than 1, our series converges, and that's really all that we need to know. So when we take our limit as n approaches infinity of these two terms in absolute value, if that is less than 1, then our series converges for any series. So that's what we are going to be using for determining convergence of a series. That would be an infinite series. We would be using the ratio technique. So number 1, we have the Taylor series for natural log, which is right here. And I believe that's centered around x is not 1, 0 maybe? Looks like 2 actually. Okay, so here's our Taylor series for natural log. Apologies. So we're going to let L be this limit, and we're going to plug in our information into this term sub n plus 1 and term sub n. So this one right here, that is our t sub n. This, you see by my exponent how I'm deciding this, this is our t sub n plus 1. So that's the next term after the nth term, the n plus 1th term, I think is how we say it. Now, let's evaluate this limit. So my limit as n approaches infinity of the n plus 1th term, so that's negative 1 raised to the n plus 2 over n plus 1 times x minus 1 raised to the n plus 1 all over negative 1 raised to the n plus 1 over n times x minus 1 raised to the n, and that thing needs to be an absolute value. That's the one thing that I always forget until the end, but it needs to be there at the beginning. Now, one of the questions in this is at the bottom, and it says, what happens to the negative 1 raised to the n plus 1 and the negative 1 raised to the n plus 2? Well, with the absolute value, I don't care whether any term is positive or negative, because the whole thing's going to end up being positive. So my negative 1s are not relevant when I am evaluating the ratio test, because we are an absolute value. Eventually everything just has to be positive anyway. So let's rewrite our limit, and let's do a little bit of simplifying. We've already done some. We've gotten rid of that negative 1 raised to the n plus 2 and the negative 1 raised to the n plus 1. Now I'm going to deal with the top. The top has an x minus 1 raised to the n plus 1, and the top actually also has this n that's on the bottom down here. Again, when I have a fraction divided by a fraction, I take the bottom fraction, flip it, and multiply. So that n ends up here on the top. And then in my denominator, I have this x minus 1 raised to the n is still in my denominator. And then I still have my n plus 1. I need to put that in parentheses then. And we're still absolute value of that. Now, that top blue x minus 1 raised to the n plus 1 and that green x minus 1 raised to the n should simplify. So let's rewrite it a little bit so it looks more like it's going to simplify. So that's going to be x minus 1 raised to the n times x minus 1 raised to the first. That's the same as x minus 1 raised to the n plus 1 times n over x minus 1 to the n times n plus 1. And I think you can see now why I did that. It's very easy to see that the top x minus 1 raised to the n and the bottom x minus 1 raised to the n should simplify to a special version of the number 1. So I still have my limit as n approaches infinity, and now on the top I have x minus 1, and then I'm multiplying that by n over n plus 1. Again, we're still in absolute value. Now this is where I have to pay attention to what my variable is in this limit. The x actually isn't my variable in this limit, the n is, because I'm evaluating this limit as n approaches infinity. So I can rewrite this as the absolute value of x minus 1 can come out. Then I have the limit as n approaches infinity of n over n plus 1 in absolute value. So I look at that and I say, okay, so I plug it in infinity, and when I do that, I get an infinity on the top and I get an infinity on the bottom, and oh, I'm so bummed out, I can't evaluate it. And I go, wait. I remember a rule from calculus class that I used to call L'Hospital, even though it's L'Hôpital's, and I can use that rule to evaluate this limit by taking the derivative of the top and the derivative of the bottom. So now I have that my limit is this x minus 1 in absolute value is still outside. My limit as n approaches infinity of the derivative of the top, which is 1, over the derivative of the bottom, which is 1. So at this point I have my limit, and my limit is the absolute value of x minus 1. So great, I've got my limit. Now I'm going to move on to the top of the next page. And when I do, we're writing in an equality. I want this limit to be less than 1. Remember our ratio test. As long as that limit is less than 1, my series converges. So absolute value of x minus 1, I want that to be less than 1. I lost my absolute value symbol. When I solve that, it's really x minus 1 has to be between 1 and negative 1. I add 1 to everything to get x by itself, and I get 0 less than x less than 2. So this is our open interval of convergence. Okay, so I know that the Taylor series, I'm going to scroll down a little bit, this Taylor series that I have here will match up with natural log of x. They should be the same as long as my x is between 0 and 2. So that's what that means. So number 3 says, let's go ahead and take a look and see if they actually do converge. Now I've got this graphed, so I'm just going to pull this graph up. So what I have is I have s sub 10 typed in, which is to the 10th term of my Taylor series, and I have natural log of x typed in as well. So let's see what that looks like. And here are the two graphs. The natural log of x is the thick graph, and I think you can tell that we're pretty accurate. Somewhere around in here we start being accurate, sorry, at 0, and we're still accurate to somewhere around in there, which I'm guessing is at 2. So take a moment, sketch those two on that grid that you have. And what I'm going to do with my grapher is I'm going to graph the next thing. So you go ahead and sketch. Hopefully you have an idea of what it looks like. And I'm going to go ahead and I'm going to sketch the next thing on my graph, which is natural log. Oh, I want to graph the other one as well, which is the 10th, sorry, s sub 11. I was supposed to put it on path style, but I didn't, so I'm going to leave the natural log up there. The s sub 10 is up there, and then what is also graphing right now is s sub 11, which is nearly impossible to even see. We aren't going to actually see it until we get past x is 2, and then our s sub 11 is going to show up. We're going to look at the differences between that. And when you see that s sub 11 show up, you can see the end behavior as x approaches infinity is completely opposite of the s sub 10, which should make sense. An odd function would have opposite end behaviors, whereas an even function would have the same end behaviors as x approaches infinity and negative infinity. So that's what it's asking for in number 4 is, well, what is the difference between the two? But what's most important is you can see that these three graphs are identical between x is 0 and x is 2. Okay, so that was the whole point of that. Feel free to write down whatever it is you'd like about that. We are not going to do number 5 on this handout. we are moving on. Again, you have the answers to that handout, so if you want to copy that stuff down, you're welcome to. I'm moving on to the page that says ratio test. So for ratio test, we have this idea of absolute convergence. And if the series absolute value of a single term converges, then the series considered convergent absolutely. And once we know that the absolute value converges, then I know that the series converges as well. We're going to deal with that a bit later. So we have the ratio test. These are our three scenarios. We have if the limit is less than 1, a series converges there. If the series is greater than, the limit is greater than 1, then the series diverges. And if that limit is ever equal to 1, this test doesn't work and we have to use a different test. We're going to talk about different tests on a different day. All we're doing is ratio tests right now. So note, factorials, they factor out. The top and bottoms factor out. It's great. Exponential functions, they factor out as well. So those two things are awesome for the ratio test. And if you just like working algebra, ratio test is the way to go. So the next example is show that the power series for sine of x converges for all real values of x. Well, okay, let's see what that is. Because we remember our sine of x, sine of x is equal to the sum from n is 0 to infinity of -1 raised to the n x to the 2n plus 1 over the quantity 2n plus 1 factorial. So we see that factorial, we get all excited, yay, we got a factorial, we want to do a ratio test. Okay, let's do our ratio test. So my limit L is going to be the limit as n approaches infinity of the n plus 1 term, which I may run out of space on this. So that's going to be x raised to the 2 times n plus 1 plus 1 over 2 times n plus 1 plus 1 factorial all over the nth term, which is x to the 2n plus 1 over 2n plus 1 factorial. Shoo, okay. So absolute value, that's that thing I always forget. So this is going to be equal to the limit as n approaches infinity, and we need to simplify this. I'm going to flip my fraction that's on the bottom and multiply by the top. I'm going to expand my 2 times n plus 1, figure out what that is. So that first term is my x. So I now have x raised to the 2n plus 2 plus 1 to the 2n plus 3. And additionally on top, I'm going to have that thing that's on the very, very bottom, that 2n plus 1 factorial. Okay, so that's what I got on the top. In the bottom, I'm going to deal with my x term first, and that is just x to the 2n plus 1. And then my factorial in here is going to be 2n plus 3 factorial. So that's what I mean. If you like to do the algebra, the manipulation, this is for you, absolutely. Oh, you know what? I didn't even put my -1s in there, so technically they should be in there. I forgot that. -1 to the n plus 1 and -1 to the n, but ultimately I know it doesn't matter, so I didn't even write it down. Apology. So let's see what we can simplify here. We actually can simplify some things already. So I have the limit as n approaches infinity. I really don't know why I wrote that there. It's not going to fit. Limit as n approaches infinity. On the top, I'm going to rewrite that as x to the 2n plus 1 times x to the 2. So if I were to multiply that together, I would get 2n, x to the 2n plus 3. And on the top, I have a 2n plus 1 factorial. In my denominator, I have my x to the 2n plus 1. And in the denominator, I also have, I'm going to rewrite my factorial, and I'm going to write a little side note down here. So 2n plus 3 factorial is going to be 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n dot 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 dot. Now what's important is this thing right here, that's the same as 2n plus 1 factorial. So I can rewrite my 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So I just write it out until I get to the factorial that I have on the top. Let me erase my little note. So this is what we have. Don't forget your absolute values. Okay, so now I can start simplifying things. And when I simplify this, I get the limit as n approaches infinity of x squared on the top. On the bottom, I have the 2n plus 3 times 2n plus 2. I'm going to go ahead and multiply that out because I know I need to know what it actually is. Actually, I don't have to, but I'm going to anyway. So I have 4n squared plus 10n plus 6 in absolute value. And again, n is approaching infinity. So this x squared is not relevant to the limit, so I can pull that out. Limit as n approaches infinity of 1 over this 4n squared plus 10n plus 6. That's also an absolute value. Now, as n approaches infinity, that thing is trying to become 1 over 0. 1 over infinity, my bad. 1 over infinity, which means 1 over infinity is trying to become 0, which means this limit is equal to 0. So, let's go back to our ratio test. We got the limit was equal to 0. I'm going to scroll back up. I scroll back up. The series converges if L is less than 1. 0, less than 1, which means this series converges. Beautiful. Okay, so series converges. And this one converges for all x. That makes us happy. Okay, so we have a couple other special cases with our ratio test. If we get a radius of convergence, which we're about to do, and the radius is 0, the series converges only for x equals a. So that's when we get our limit is equal to infinity. If our limit is equal to infinity, that means that the series converges only at a single a value, at the one value it was centered about. Part B, if r is infinite, then the series converges for all values of x. That means when we get the limit is equal to 0, automatically means for every single value of x that I plug in, the series is going to converge. Important thing to know. Okay, turning the page. So find the radius of convergence for this thing. So let's go ahead and use our ratio test. So what I would like for you to do, now this is a different question, it's asking for the radius of convergence. So what I would like for you to do is actually use the ratio test, set your limit less than 1, and solve for x. Once you get there, I want you to pause it, play the video again, so we can talk about what the radius of convergence is. So right now, do the ratio test on this first example. So I totally ran out of room, I apologize. So here is my work evaluating the limit, and my ultimate limit that I got was over here, absolute value of x over 10. Then from there I went up to the very, very tippy top on the left, and I said, well, this is going to converge as long as that is less than 1. So I solved for x, and I said x is between negative 10 and 10. So if you need to pause the video at this point to get your work straight, go ahead and do that now. The question is find the radius of convergence. So basically what we have going on is we have x has to be in between negative 10 and 10. So this is my diameter. My diameter is 20 all the way across, which means my radius is half of that, which is 10. This one was nice because it was centered about 0. Not all of them will be centered about 0, but that's what I mean by finding the radius of convergence. Sorry, if you need to pause the video here. What I'd like for you to do now is we're going to do the next example together. So for the next example, I can do the ratio test if I would like. However, this thing is geometric. If you were to look at this series is equal to 1 plus x to the 1 plus x to the 2 plus x to the 3, where a sub 1, the first term is 1. My ratio is x. And as long as my ratio is less than 1, my geometric series will converge. So as long as this is less than 1, and again, this is just a geometric series rule. That's all I'm doing right here. So if I recognize that, it makes it so much easier. This means that x is between 1 and -1. Again, I look at that, -1 to 1. That's a 1, not an I. This distance is 2, which means my radius is 1. And again, that one's centered about 0. Next example, I would like for you to try this one. And again, this one, I don't know if this is geometric or not. It probably could be. I did this as a ratio test, so I'd like you to try this example. So pause the video now and do that example. So for this one, I ended up with the radius is 1. It's in the circle. It's hard to read, but what it's here, let's just fix it. This says the radius is equal to 1. So if you did not get that, pause the video now and fix any of your work. Moving on to the next example. Again, we're doing a radius of convergence, and again, I would like for you to try this one as well. So you go ahead and try this example. Pause the video now, please. So here is my solution. Here's my solution to the example. I got my radius of convergence was 1/4. So pause the video here if you had any questions. I'm going to move on to the last example. And what I mean by that is you have one more to do. So again, you are going to do this one. You try and do this. So pause the video now, please. Here's my solution. I got the radius of convergence is 1/3. If you did not get that, please pause the video here and look at my work and see if you can find your mistake. Please write down any questions that you have on this video lesson and bring them to class. Have a wonderful evening.